and in this video we're going to be covering the derivation of center of gravity. So I'm going to start off by deriving the different equations for finding centroids. There are different centroid equations such as the center of gravity, center of mass, centroid of a volume, centroid of a line, and the most common one being the centroid of an area. So for the purposes of this video, I'm only going to derive the center of gravity equations since the other centroid equations follow the same general process. So to begin, we're going to go ahead and write a couple definitions down. So the first one is going to be a centroid. So we define centroid as the geometric center of a body. And note that with the centroid, sometimes the centroid is also the same as the center of mass. Or also the center of gravity. But this is only true if the material of the body is uniform. Okay, and then the other definition we're going to write down is the center of gravity. And we're defining that as a resultant point where the weight of the body acts. Okay, now with those out of the way, we can go ahead and start the derivation here. So we're going to say that we have this body here. We have our y-axis, we have our x-axis, and we have our body. Okay. And we're going to say that this body is composed of an infinite number of particles with a differential size. So there are these small particles here that make up this body all throughout. And each of these particles, we're going to say is going to have a weight dW. So dW, each of these tiny particles is going to have that weight. And we know the total weight of the entire body is W. So we'll call the total weight W. And we can also say that the total weight is also the sum of all these tiny infinite pieces, which we can write the sum as the integral dW, meaning the sum of all the tiny dWs will equal the overall weight of the body. Okay, with that, now we can go ahead and find the centroids of the body. So let's look at one axis at a time. Focusing on the x-coordinate for centroid, the location, which is going to be measured from the y-axis, can be found by the moment caused by the force W times the moment arm. So if we have, let's say this was our centroid here. The moment arm for this centroid, since we're measuring it from the y-axis, is going to be this distance here. And we're going to call that is going to be our x bar. So I just drew a point here representing our centroid. In this case, the distance from our centroid to the y-axis will be denoted as x bar and is what we want to find. We set the following expression W times x bar. So we know this is a moment. We're going to set that equal to the sum of the moments of the weights of all the particles. So each of these particles right here, so let's take this one for instance. We're going to say each of these particles also have a moment arm, and their moment arms are going to be represented by x tilde here. So each of these tiny particles has an x tilde moment arm, and if you take the sum of all their moments, that's going to equal the moment w times x bar. So integral of dw times x bar, or I'm sorry, x tilde. That right there is the sum of the moments from all, we'll call them particles. That is going to be equal to the net x bar from the center of mass times the weight. Now, since we want to find the centroid, that means we're looking for x bar. In order to get x bar, we simply rearrange the equation, this equation right here, in terms of x bar. So let's go ahead and do that. Sorry. Okay. Finally, remember that we said the overall weight of the body, W, can be represented by the integral dW from before. So in that case, we can rewrite this even further. Okay. So now we have the x bar equation to find one coordinate of the centroid. The same expression can be written for the y and z coordinates as well. So this right here is our x bar. Likewise, y bar and z bar. Sorry about that, these are tildes, not bars. So those are your centroid equations for each coordinate, the x, y, and z. Now if you wanted to find a different centroid, the derivation is going to be the same process. You would still just equate the moment caused by the differential elements to the moment caused by the overall weight and its moment arm. The equations are the same except for the differential elements. I'm just going to write the other equations for x bar down, since y bar and z bar are essentially the same equations. So for center of mass, our x bar equation is going to be the following. Integral of x bar dm over integral dm. For centroid of a volume, our x bar is going to equal integral of x bar, or I'm sorry, x tilde dv over integral dv. That's a tilde for center of mass. Sorry about that. And then centroid of an area, x bar is going to equal the integral of x tilde dA all over integral dA. And then finally, centroid of a line, x bar is going to equal integral x tilde dl over integral dl. So that right there are all your x bar equations for different centroids. And like I said, the y bar and the z bar are going to be essentially the same equation, just looking at a different axis. All right, I hope you guys enjoyed this video.